Okay. So, welcome to the lecture of this finite volume method. Now, if you put these things back in the algorithm, what will happen? So, first thing that I will have u1 j equals to a1 j, for which j goes from 1 to n. Then I get L I1 equals to a I1 by u11, where I goes from 2 to n. So, these two elements initially are being computed, and then you go over loop for I goes 2 to n minus 1, then u I j equals to a I j minus k equals to 1 to I minus 1 L I k u k j, where j goes from I plus 1 so on n, and the lower triangular system is a k I minus summation of j equals to 1 to I minus 1 L k j u j I, where k goes from I plus 1, I plus 2 so on n. So, that is where the loop closes, and finally, you get u n n equals to a n n minus I goes to n minus 1 L n I u I 1. So, that is how the whole algorithm works. Then you obtain from A getting decomposed into two component lower and upper triangular system, and once you get that, then you have to get the solution for that. So, now the steps which are required is the substitution step. Okay. So, now my A got into L and U, one is lower and upper triangular system, and first need to calculate the vector C, so that through forward substitution process, where you get C1 equals to B1 and Ci equals to Bi minus j equals to 1 to I minus 1 L I j C j, where goes to 2, 3 to n. So, that is where you get the, and the next step you get the values of phi by back substitution process, which will be phi n equals to C n divided by u n n, and phi I equals to C I minus j equals to I plus 1 to n u I j phi j divided by u I I. So, where I goes n minus 1, n minus 2 to 1 like that. So, initially first step, this is your first step where you get the forward substitution to get the vector C, and the second step you do the backward substitution to get the. So, essentially you had A equals to L u, and where this was solved for B, and it was written L u C equals to B, and from there you get the solution. Now, the important points are few here, like the elements of this L and U can be directly stored in the matrix A if it is no longer needed. This is because that A are only needed when the corresponding elements of either L or U are calculated. So, the number of operations required to perform here, the number of operation which are required to perform for LU factorization for a system of n by n is 2 something n cube by 3. So, which is double the operation that is required to solve through the Gauss elimination process. Again, the advantage of this LU factorization is that when the same matrix A applies to different B, then no need to calculate L and U factorizations again and again, the coefficients just can be directly applied to. So, which makes the solver more efficient. Now, one can obtain this LU factorization through Gauss elimination process. So, LU decomposition by Gauss elimination. So, that is another way of obtaining the thing, and so this is sometimes can be also used in some CFD codes. Now, if you look at that algorithm, how you do that? You have simple U1j equals to A1j, where j goes from 1 to n. Now, you go over loop for k equals to 1 to n minus 1, you obtain I equals to k plus 1 to n, where L ik equals to A ik divided by A kk, and then here you start, then you get for j goes from k plus 1 to n, u ij equals to A ij minus L ik multiplied with A kj. Then you closes that loop, which will get you this information, and then the upper one and the last one. So, that is where the Gauss elimination process can be also used. Now, the important points. So, this is possible, all this Gauss elimination or LU factorizations when you have a generic key. Now, one can look at this method for, or rather the direct approach for banded sparse matrices. So, this would be very specific case, because what we have discussed so far is in more generic approach, because irrespective of what is the property of A, we did the Gauss elimination or we could do the LU factorization. Now, when you say that the banded sparse matrices, that means the matrix A which is sitting here, it could be looking either some sort of a band like that or some sort of a band like that, or so the solvers which can be used for this case cannot be generalized for the elimination process. In this category, the first one which we will talk about is the tridiagonal matrix algorithm, which is called TDMA. And what happens? This algorithm is known as the Thomas algorithm, and it is a very common and old algorithm which was, or rather often discussed in any CFD, but it has some specific application for a particular banded system like trigonal system. This is one of the efficient solver. How you get it? Let us say you consider this cell like that, starts from I you have 2, 1, 3, 4, these are the points, and so on, you get n minus 1. So, number of points n and then the cell centers value. So, the coefficient matrix for this kind of system, if one has to write ai phi I plus bi phi I plus 1 ci phi I minus 1 equals to di, where I goes from 1 to dot 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 n c 1 0. So, what one can do for I equals to 1, you can directly solve this equation a 1 phi 1 equals to minus b 1 phi 2 plus d 1, which you can see phi 1 can be solved minus b 1 by a 1 by phi 2 plus d 1 by a 1. Similarly, for I 2, if one has to write, he will get a 2 phi 2 equals to minus b 2 phi 3 c 2 phi 1 plus d 2, which will get you the equation for phi 2, which is minus a 1 b 2 a 1 a 2 minus c 2 b 1 into phi 3 plus d 2 a 1 minus c 2 d 2 d 1 divided by a 1 a 2 c 2 b 1. So, if one generalize this, then one can write phi I equals to p I phi I plus 1 plus q I. So, that is the generic formula for any I where I goes from 1 to n. Now, if you combine with the equation I plus 1, then p I minus 1 equals to p I minus 1 plus q I minus 1 a I phi I plus b I phi I plus 1 plus c I phi I minus 1 equals to d I. So, from here you get phi I equals to b I a I plus c I p I minus 1 phi I plus 1 plus d I minus c I q I minus 1 divided by a I plus. So, that is what you get. Now, if you compare this one and the previous one, you can see that p I is nothing but b I divided by a I plus c I p I minus 1 and q I is d I minus c I q I minus 1 by a I my plus c I p I minus 1. In both these cases, I goes from 1 to n. Now, for I equals to 1, you can get p 1 equals to minus b 1 by a 1 and q 1 equals to d 1 by a 1. And similarly, for I equals to n, you get, since b n equals to 0, you get p n equals to 0, phi n equals to q n. So, that is how the algorithm works. Actually, for a system like that, you can, if you put in the algorithm, then it would be quite handy for this kind of banded system. Now, the second one which could be also of interesting is the pentadiagonal matrix algorithm, which actually talks about PDMA. Previous one was the TDMA, this case called the PDMA, and again this one you get. See, the TDMA one can obtain if somebody discretize the diffusion equation in one dimension. Now, someone discretize the diffusion equation in two dimensional system, he gets essentially this kind of a pentadiagonal system. That means not 3, you have 5 banded system. So, this is called the pentadiagonal system, and in two dimensional the diffusion equation discretization can lead to this kind of situation. Now, once you get this kind of a PDMA, so you can have a very specific solver which can actually be used for this kind of solution. And if one uses the notation, very standard notation, and like the one which we have used here, the I goes from 1 to n, then the equation system for pentadiagonal system would be AI phi I plus BI phi I plus 2 plus CI phi I plus 1 plus DI phi I minus 1 plus EI I minus 2 equals to Fi, where I goes 1, 2 to n. If you see the base variable at ith, it is equally distributed between I plus 1, I minus 1, I plus 2, I minus 2, and there are coefficients associated with it. So, this is the equation which has the 5 points I plus 1, I plus 2, I minus 1, I minus 2, that leads to a pentadiagonal system. This is called the 5-point stencil, and which is this particular one is subjected to D1 equals to E1 equals to E2 equals to 0, and Bn minus 1 equals to Bn equals to Cn equals to also 0. So, it has very specific system. Now, if you write for I equals to 1, this particular one, it gives you back phi 1 equals to minus B1 by A1 phi 3 minus C1 by A1 phi 2 plus F1 by A1. Now, similarly for I equals to 2, the phi 2 can be obtained minus A1 B2 divided by A1 A2 minus D2 C1 minus, so this is multiplied by phi 4 minus A1 C2 minus B1 D2 divided by A1 A2 minus D2 C1 phi 3 plus A1 F2 minus D2 F1 by A1 A2 minus D2 C1. So, this essentially you put the values of I in this equation, and then you start obtaining individual ones. So, if this way one can proceed, then he can write an generic expression for phi. So, in generalized form or rather generic form, one can write that phi I equals to Pi phi I plus 2 plus Qi phi I plus 1 plus Ri. So, which goes for a loop I equals to 1 2 to n. Now, you compute phi I minus 1 and phi I minus 2 using this equation. So, essentially using this you compute that, and then from there you obtain phi I equals to, it would be B I A I. So, with a minus sign sitting there, A I plus E I P I minus 2 plus D I plus E I Q I minus 2 Q I minus 1 phi I plus 2. So, that is the first term, and the second term would be minus C I plus D I plus E I Q I minus 2 into P I minus 1 divided by A I plus E I P I minus 2 plus D I E I Q I minus 2 Q I minus 1 into I plus 1 plus F I minus E I R I minus 2 minus D I plus E I Q I minus 2 R I minus 1 divided by A I plus E I P I minus 2 plus D I E I Q I minus 2 Q I minus 1. So, you get an generic expression for phi I or the ith element of that component. Now, if you compare this one with this equation, so this is one equation for phi I, and here is an expression which we have written the generic expression, and if you compare them together, you get Pi is essentially nothing but minus Bi by Ai plus Ei Pi minus 2 plus Di Qi minus 1. Similarly, one can write Qi equals to minus, it is Ci plus Di Ei Qi minus 2 Pi minus 1, and in the denominator you have the same expression Ei Pi minus 2 plus Di plus Ei Qi minus 2 Qi minus 1, and the last one is the Ri, which is Fi minus Ei R minus 2 Di plus Ei Q I minus 2 into R I minus 1. So, and the denominator is the same, Ai plus Ei plus Di Qi minus 1. Now, with for I equals to 1 and 2 which can get you the specific expression like P1 equals to minus B1 by A1, Q1 equals to minus C1 by A1, R1 equals to F1 by A1. Same thing you can get P2 equals to minus B2 divided by A2 plus D2 Q1, Q2 equals to minus C2 plus D2 P1, and R2 equals to F2 minus D2 R1 divided by A2 plus D2 Q1. So, in this particular expression, if you put I equals to 1 or 2, you can get back these specific numbers, and since you have Bn minus 1 equals to Bn equals to Cn equals to 0, which will actually lead to Pn minus 1 Pn equals to Qn equals to 0. So, from here one can find out phi n minus 1 and phi n can be found using this information. And what could be that? Once you get these two, phi I equals to R n and phi n minus 1 equals to Q n minus 1 Q n plus R n minus 1. So, the specific ones one can compute. So, all these expressions, if you put it back in the system, then you can get the. So, the compute algorithm, if somebody sees, you first compute P1, Q1, R1, P2, Q2 and R2, and then what you do for I goes from 3, 4 to n, use forward recursion to compute the values of Pi, Qi and Ri. Then you compute phi n and phi n minus 1, and then finally for I n minus 2 to 3 to 1, you use backward recursion to compute the values of Qi. So, that is the essentially complete pentadiagonal algorithm. So, what you get, first you obtain this specific one P1, Q1, R1, P2, all these expressions, and then you go for the forward recursion, and once you go for the forward recursion, as we have obtained here, all these Pi, Qi, Ri you obtain, and once you obtain all these, you go and calculate the phi n and phi n minus 1 using this, and then finally you go for the backward recursion to compute the value of Qi. So, this completes the algorithm for the pentadiagonal. So, these are the discussion on direct approach. Now, in the next lecture we carry on the iterative process. Thank you.